Hi, can you hear me? I guess so. So, AsmFX is our proposal for an abstract assembly language with primitive effect handlers. And by abstract assembly language, I mean that it is an extension for assembly languages, but it doesn't specify as a base any assembly language. It doesn't specify a set of general purpose registers, and generally it's not imagined to be implemented directly as an instruction set architecture. Now, a bit of motivation. Effect handlers are a programming language feature that can be used to implement error handling, other things like non-determinism or dynamic binding, concurrency, probabilistic programming. So effect handlers are great. They are typically implemented on top of other fairly high-level language features like first-class functions, closures, continuations, prompts. So all of these things are fairly away from a typical hardware implementation. So they need to be translated, and you can ask yourself, what is the simplest abstraction over an instruction set that we need to implement effect handlers? Now, maybe you could ask, why are we even interested in this? In our case, we have an interest in understanding the potential relationship between effect handlers and new hardware features like hardware capabilities in architectures like Cherry. And in order to do that, it was important for us to develop a language that is both very close to a hardware implementation and still presents a primitive notion of effect handlers. Another question that you can ask yourselves is, if we have primitive effect handlers, can we actually implement some of those high-level features on top of effect handlers? Now, before proceeding, I want to start with a bit of terminology. So that's the anatomy of a typical program fragment that uses effect handlers. And the topmost part that in the slide is in blue can be any part of the code that wants to set up an effect handler and run some code under that effect handler. And I call that external code. The code that is run under the effect handler is what I call client code, and it's code that can perform effectful operations like that HOPE24. And the handler itself is composed of a single return clause and possibly many clauses to implement effectful operations that I call operation code. And in the diagram, you see all the possible transitions that we have between those fragments of code. So from the external code, you invoke the client code, and the client code can either return immediately to the external code but in order to do that, it'll invoke the return clause for some potential post-processing. Otherwise, it can also invoke an effectful operation, and the effectful operation can either resume the client code, or it can abort abnormally the computation, returning immediately to the external code. Now, so this is what you would have in a high-level language. When we translate this to AsmFX, two things happen. The first thing is that we started with the structured code, and now we have destructured it in 4 different flat fragments of code, each representing one of the main categories that I discussed before. And the other thing is that each of those 6 arrows, of those 6 potential transitions between the code parts, has been converted to a specific assembly instruction. So, for example, to perform a transition from external code and to client code, installing a handler, we have an enter instruction. When we want to perform an effectful operation, we use the instruction do that makes a transition between client code and an operation clause. When the client code has finished its computation and wants to return a value, we have a return instruction that invokes the return clause of the handler. The return clause of the handler can finally make a transition back into the external code with exit. And as for the operation clause, resume is used to invoke the resumption into the client, whereas break is used to terminate the operation clause abnormally and return to the external code. Okay, before discussing the semantics of these operations, I want to use a slightly more complex example that is, that is the one that you can see here. This is a budget handler that uses a global variable, mutable variable, that represents a certain budget of resources. And the idea is that this handler is used to ensure that a certain code will run under limited resources. So, for example, in this code, the client first charges the budget by an amount of 10, then performs some other external operations that can also charge the budget, and finally returns some value based on the result of those operations. And the handler itself will, when the charge operation is invoked, will reduce the budget by the specified amount if there is enough budget, and then resume the computation. But if there isn't enough budget, it'll just abort the computation, return a dummy value of 0, and it'll also return the value -1 as the budget, as the final budget, to specify that the budget was completely used and was not enough to finish the computation. And we can compile that to AsmFX. That's a partial version of the actual code. Now, what I have described to you is a set of 6 instructions that you see there. And to specify the semantics of these instructions, we actually propose an abstract machine that implements them. And I'm not going to show it here, not because it's too complicated, but because it wouldn't be the best way to explain it. But what I want you to know is that the abstract machine is based on a concept that is the effect context, which is a data structure that is used to specify the current effect handling state of the computation. And there is a nice thing about this data structure, which is that it can be implemented as a contiguous block of memory that grows and shrinks at one end. All right, and I can show you the gist of this, of the abstract machine. So, for example, if we want to install a handler with the enter instruction, first of all, we are running in any initial effect context, because we can perform an enter instruction in whatever state. And when we execute the instruction, what happens? Well, we have to install the handler in the context and also install a reference to the code that must be executed after the client code under the handler is done. So we do that by installing two records in the effect context, one with the address exit that represents the computation after the client code, and one containing pointers to the closes of the handler. And finally, we perform a jump to the client code, so we update the program counter. Now, let's have a look at do. Well, a do operation, an effectful operation, will run necessarily under a handler that must implement that operation, and also because of some well-formatness conditions under a certain leave record that is associated with that handler. But not just that. After installing that particular handler, for example, we may have installed more handlers. So there is potentially some more context that is represented there by delimited context, by the delimited context block. And what happens when we perform the do instruction? Well, we have to install a reference to the resumption that the operation clause can invoke, which is a continuation block R, and you can see that I have also added a label R to the code to denote where we will jump when we perform when we invoke the resumption. But when we invoke the resumption, we also need to restore the previous context. So the continuation record will have to include the part of the context that we have removed so that we can restore it later. And in fact, that's, oh yes, and the final thing is we jump to the operation clause that implements charge. Now, finally, the opposite operation, resume. Again, this needs to have a resumption continuation in the effect context, but there can be more stuff in it. So there is a delimited context that represents the additional context within the handler, which is separate from the delimited context of the continuation that will be restored once we invoke the continuation. And when we perform resume, we just forget about the delimited context of the handler, because we are never jumping back to the handler, and we restore the context that was stored in the continuation record. And finally, we jump to the address of the resumption. What I have just described to you is enough to implement a fine tail resumptive handlers. That means the resumption can be called at most once as the final operation of the handler code. And this is also known in the literature as runners. But can we do more? Can we do handlers with state? This is often in the literature implemented by means of parameterized handlers. Can we do non-tail resumptive handlers, handlers where the resumption is not called as the final operation of an operation handler? And can we allow multi-shot resumptions which are invoked more than once? Well, before going there, I want to talk about something that is not strictly related to handlers, but it comes up when using handlers in AsmFX, which is saving and restoring registers. And there are several situations in effect handling code where we want to save or restore registers. For example, when external code enters a handler, it's got a certain state in its registers, and it may expect that state to be retained after the client code is done. So there is a need to restore that environment. Furthermore, state, handler code might want to have a persistent state across effect calls, and that means that each operation clause must restore and save the state at the beginning and the end of its work. And finally, client code that calls into an effectful operation typically still wants to retain its state, so it will also need to save and restore its state. And it turns out that there is a very clean way of doing this by equipping each of the types of records that I have shown you at the beginning that compose the effect context with a set of register values that can be used to save and restore the registers in the situations that I have just mentioned. And you can probably see that since those records essentially contain code addresses, and the register part is a set of values, this is essentially the same notion as a closure, okay? Now I'm going to show you a few more involved examples. So this is again based on the budget example, but here I'm showing you that I initially implemented it by means of a static variable that is located in main memory. In an effectful programming language, typically we would use parameterized handlers, that is, handlers that have a parameter that is set up to an initial value when installing the handler, and can be modified each time a resumption is invoked. In AsmFX, we can express the state by means of state registers that, quite similarly to parameterized handlers, are added to the enter instruction that installs the handler, and are automatically updated upon the execution of the resume instruction. And an important thing here is that this state is stored in the effect context, and the effect context is not located in main memory. It's a different data structure altogether that is not accessible as main memory by the instruction set. And that guarantees that the state can only be updated by effect handler code and not by the client, for example. So, now, another thing that we can do in AsmFX for free, essentially, is recursion. Well, recursion needs two things. One is function calls, and the function calls, it shouldn't be surprising that we can implement them with effect handlers, because you can see that handling a value with a trivial handler that only has a return clause closely corresponds to the beta rule. But to perform recursion, we also need a stack to store the environment for each active recursive call. So you see on the left recursive implementation of the Fibonacci sequence. Turns out that we can do that very easily in AsmFX, because by means of saved registers specified in the enter instruction, we can use the effect context as the call stack. And so, as I was saying, the saved registers are specified by the enter instruction and restored automatically by exit immediately before function return. A final example I have here is for multi-shot resumptions. Here I have a propositional statement that happens to be a tautology, A and B, or not A or not B. It's implemented by means of non-determinism, in the sense that for each of the propositional variables, we flip a coin and then return. I'm sorry, this is going forward without my consent. The proposition, then after taking a non-deterministic value for the propositional variables, we compute the propositional statement. And we run this under a tautology handler that uses non-determinism to evaluate all the possible evaluations for all the possible truth values of the propositional variables. And in particular, this handler uses resumptions in a multi-shot way by evaluating each propositional variable as false and true, and taking the conjunction of all the possible evaluations. And this is guaranteed for tautologies to return true and false for non-tautologies. Now, as I was saying, with resume, with the instruction resume, we cannot do that, because resume immediately sends the return value to the return clause and does not allow you to return to the effect handler code. So we actually support multi-shot resumptions by means of additional instructions called reenter and final reenter, which send the return value back to the handler code that invoked the resumption. And this is how it works. And interestingly, we can also specify saved registers, because now that we can return to handler code, the handler has can have some registers to save. So this is a summary of all the resumption instructions. Resume is the simplest one, and doesn't put in the effect context any information on the invoking code, and only allows a single tail call to the resumption. Final reenter stores an additional leave record in the context with the return address into the effect handlers, and thanks to that, it can allow a single non-tail call to the resumption. And finally, re-enter allows multiple non-tail calls by duplicating both handler and leave records. And there are also shallow variants that allow to replace the handler when we invoke the resumption. And now, finally, it's time to conclude. So what I have presented to you is a self-contained instruction set extension to implement effect handlers. And the important thing is the concept of effect context as the data structure that implements effect handling. We support some more advanced features like parameterized handlers, multi-shot resumptions, and shallow handlers. And what I have presented to you is actually implemented. It's a prototype, nothing fancy, but it's available to test if you want. And now, what we cannot do yet, but we are working to be able to do. One thing is storing continuations for future use, which is needed for example, for concurrency, and named handlers. And probably similar changes are needed for both concepts. However, I have a gut feeling that it's not entirely straightforward, and some work is needed. This is all for my talk. Thank you for listening.
Thank you. Do we have questions?
Hi. One thing you can do to implement handlers in a slightly simpler way is that you can just make the return clause one of the handler clauses, right?
Yes. OK.
So I just, just where you never use resume, right? And it would make it slightly simpler as an architecture set extension. So I just wonder if you had targets in mind where you could take advantage of the fact that those are two different things and implement one of them more efficiently.
All right. We did consider that. It's definitely possible to do that. The question is whether
I guess the question is why not
is exactly the same thing as an operation clause. Okay.
Exactly. Yeah.
One thing that you have to consider is that a return clause must not have access to the resumption, otherwise it's not a return clause. If you implemented it exactly as an operation clause, you would not be able to guarantee that. Nothing terrible, I suppose, because it's still an assembly language, and you are not supposed to prevent the user from doing stupid things. But in our opinion, it was a cleaner way to implement it by keeping things separate.
Thank you.
We have time for one quick question, and maybe the second speaker can go install.
Okay, I wonder how your approach can be modified to support delimited continuation, because the difference is that with delimited continuations, I mean shift 0, reset 0, you don't have operation clauses. The do decides what code to execute, but in the context of handler.
Okay, sorry, I missed something at the beginning of your question. What is the setting that you're talking about?
Is it possible to define some similar assembly language designed for delimited continuations? I mean, for shift 0, reset 0 operators.
Okay.
Because the difference is very, very small. It's.
I'm afraid I don't know enough about that, but maybe Sam wants to interject.
We haven't thought about that in detail, but one problem there is shift and reset are very, very higher order things. You're passing in continuations and so forth. So that presupposes you already have some representation of closures. So it's not completely obvious that this framework would map directly onto that.
Thank you. So we can thanks the speaker again.
Thank you.